Welcome, everybody. In our crowd this morning, today's speaker is Dr. Edward Lin, Lin Xinwen. Dr. Lin, if I was wrong, I'm wrong, then correct me. Dr. Lin, he did his undergraduate at Tsinghua, Tsinghua Wulishi, am I right? Physics department.
Yes.
And after getting his bachelor degree, he came to NCU, National Central University, Institute of Astronomy. And I was his advisor. I remember that he told me that he was interested in astronomy. And when the problem he was very concerned is about the during Venus transit. You still remember it, right, Simon? That somehow there was a anomaly. It was a famous phenomenon in the 18th century. So he wanted to clarify this problem, and then on, he went into a number of research projects. At the end, he became expert in Kuiper Belt objects for his participation in a number of large survey at that time. And then he went to Michigan Department of Astronomy as a
Department of Physics.
Physics, okay. Department of Physics, and as a postdoc. Now he's a research scientist, and he used to work on the Dark Energy Telescope project, but now he said the project has finished. He's now working on some other more interesting things. He will talk about it. And during his study, I think he became trained himself into a machine learning expert as time goes. So we are very happy to have him, tell us his machine learning adventures. Ever, please, your talk.
Okay, thank you. Thank you for the introduction. So the topic is my machine learning adventures. Is because I'm actually not an expert, but I'm a scientist, astronomer, so I think I can share my experience and the perspective of the machine learning. So this talk will be 3-part. So first one, I will talk about my experience on the machine learning. So I use that in some research. And then I can share what I learned from those experiences. And then how do I apply that to the daily AI? We know there are AI everywhere, right? Everybody can use AI to do something. So the first part is 9 o'clock. The first part is my experience. So I'm somehow quite new for the machine learning. So my first project started from 2017, which is about 6 years ago. So at that time, we have a new project starting. It's the Hyperspring Strategic Program. So this program is mainly for the cosmology survey, I think. So you can see that they take a lot of image outside the galactic plane, and then they do the high redshift galaxy and the gravitational lensing things. But there are still a lot of asteroids pass through this field. So I think we think that we can find those asteroids from the images. The problem is that this huge survey, they take a lot of images. And then we know there are some transient source. That's what we need. The asteroids kind of transient source. But beside the transient source, there are a lot of the artifact in the images. It can be identified as a sources, but it's not. And that will confuse you once you're trying to link the asteroids through the night, right? So our first project is that can we reduce those artifacts? It could be a cosmic ray or some optical effect. But the problem is that we can easily to go through the image to see, you can see this real source, and it's junk. It's nothing there. It's the the diffraction spike. But the problem is that there are so many images and so many sources, you cannot identify that from by eye, by human, right? So we think, well, it's time to use the machine learning. So maybe machine learning can help us to identify those real source and the false source, false positive. But the step one is that you have, once you start to train the machine, you give the training set, right? You have to select some sample to train the machine. But how you can do to find the real source and the not real source and go through the machine. So what we think is that, well, if we don't go through an image, so we don't have to do by ourselves, we can just take the source catalog. It's much easier to download. And we know the real source show out every time when you observe the same spot. And the not real source or transient source is gone. But the transient source should be looked like the real source. The stationary real source. So if we can identify the stationary real source, we should be no problem for the transient source. So what we did is that we take a lot of catalog, and then we identify the scene, the object show out many times, which is the stationary, and we put that to the correct training set. And then we have to find another set of the false positive, right? And this catalog somehow provide some flag to say that if this source is failing to measure the photometric or measure the shape or measure the PSF, it's very likely the false source. So we use that part as the false state. So now we have the correct set and false state. So if we plot that, so before you're doing this, right, to see, can we separate these two different sources, the real source and the bogus, which say the false positive. So you can see in this is a magnitude distribution for these two things. It's a little bit different, but it's mostly overlap. And so you cannot separate by that part, right? You can say, oh, well, we can cut in 26 magnitude because it cannot go that faint. So in that case, we can cut here, but still we have a lot of the false positive. And the catalog provides a shape moment. So it's a shape measurement for the scene. It can compare the scene is how circle of this scene, or it's how it look like the point split function. So you can use this shape moment and plot length, so you can see the difference, right? So the real source have this very well behaved distribution, and the false positive have this strange behave distribution. But still, they have a lot of overlap. So to solve this problem, you can go to a higher dimension, right? So we can go to 2D. This is only 1D. So go to 2D. From 1D to 2D, you can see there are more separation here. So here is the photometric and the photometric error. So for the real source, it somehow have well-behaved correlation between the magnitude, how bright of it. So the brightest thing have lower photometric error. But something is wrong, right? They are quite bright, but have very large photometric error. It means it's just very likely not a real source. But still, you can see a lot of overlap. So to solve this problem, we can somehow go to even higher dimensions, because in one dimension we cannot separate them. In 2 dimensions we cannot, but maybe in some very high dimension space, you can easily separate the sources. So that's why we use the machine learning. So one way is that the decision tree, it can somehow, because human is very poor for the dimension larger than 3 dimension, right? We live in a 3 dimension world, maybe 4 dimension world, but we can only figure something out in 2 dimension. In the 3 dimension is difficult, but for machine it's not a problem. So one way we use is using the decision tree, and it's actually the random forest, which is combine a lot of decision tree. So every decision tree takes some part of the we call a feature, but it's actually the axis. So every decision tree takes several, and then you can generate a lot of decision tree and all of them have different selection of the feature of the axis. And it's somehow very democracy. So every decision tree say, well, this thing is real, this thing are not. And the second decision tree say this real, this not. So if we have 1,000 and more than half say it's real, we call that real. So it's very democracy. So we actually go to 24 dimensions. So you can see this, we have some of the shape moment, and most of them are the flux, which is the kind of photometry method. So it can be PSF photometry or the aperture photometry with different radius, different shape of radius, and the photometry error. So we put that into the random forest and somehow generate quite good result. So let's so you can see if we accept 0.05 false positive, we can reach the true positive rate about 99%. So if you go back to 2 dimension, you can see that this is this is a training set, right? And our machine learning results somehow reproduce the structure of the training set, but it can also identify this different part. So that part is somehow fail in the PSF photometry, but they somehow, part of them are real sources because they can be the galaxy or other extended sources. And this machine learning result doesn't simple cut on the magnitude. So you can see even fainter than 26, it could be real. So that's our first project. It's simple, but it's somehow quite successful to remove most of the false positive from the catalog, and we don't need to look at any images at all. So now I have my second project. So this part is in the ZTF. It's the Rayleigh Transient Factory facility, I think. So this is another sky survey, and the sky survey finding many kind of sources. So one thing interesting is the near Earth object. So they are very close to the Earth, so moving very fast. So you can somehow identify them in the images as a streak, right? So there are many streaks in the images. But the problem is that how you find those streaks. So in the ZTF pipeline, they have a method called find streak. So it's an image method to find the nice things, the streak things. But the original goal used that is to reject some false positive from the images. But it somehow also reject the near Earth asteroid and the satellite streak. So it's a junk from the cosmic survey, but it's a treasure for the asteroid people, right? So so we think that we are able to solve this problem using machine learning. But in the very beginning of this project, we do not have very good training set because there are not a lot of the asterisk, the real asterisk, because the known things is not a lot, and the survey is just starting, so we are not collect a lot of data. So what we can do is that, well, usually in trying to identify the pattern in the image, we can use the convolution neural net. But because we don't have a lot of training set, a lot of training image for the convolution neural net, so one approach is that we can put some knowledge into the image. So the knowledge is that we can modeling the shape of the asteroid trail, because we know it's a convolution of the line with the point spread function. So you can somehow write down as a math. So it's a function of length and the angle of the directions and the flux and the width of this. So the width, the length of the length of the streak and the width of the PSF. So we can somehow fit in with this function, and then we can get some flux. We can get flux. We can get the length. We can get the uncertainty on the flux, uncertainty on every measurement. So we put this into the random forest. So we figure out that most of the objects, if they are not the real asterisk, they just fail to fit. But some of them are still pass. But after we put that into a random forest, they can reject most of the things. So you can see those are the known object show up in the DTF image as the streak. And then we can identify it's a red one. And we don't identify the coarse one, the gray one. So it's simply because most of them are short. They are too short to be identified as a streak. So we are not. So the machine learning, our model don't know it's a star or it's a near Earth asteroid. But once this object is bright enough and long enough, so it's moving fast enough, we have achieved 90% of the accuracy. But it can be improved. So this is not my work, but it's further goes. It's the second version of this trick. So it's called deep streak. So it's using the convolution neural net, because now this DTF is running for a while. And then we discover a lot of near-Earth asteroids. So we have better sample to training the more complicated model. So this work is done by Doof. So you can see that once we use this convolution neural net, it have better identification for the shorter streak. And I think it's even higher efficiency for the longer streak. So we will go back to this CNN network, CNN later. But now I would like to introduce my current project. So it's a deep ecliptic exploration project. It's called DEEP. So DEEP is actually going to very deep. So we take 100 exposure, 102 2-minute exposure, and then shift and stack them to trying to find the very thin, very small Kuiper Belt object. So you can see this pointing of the deep, and then the big one is the Kuiper Belt model. So it's a resonance model. So we know the Kuiper Belt have some resonance object like Pluto, right? It's 3 to 2 resonance with the Neptune. So in the sky, so this resonance object, they close to the perihelion in some certain spot. So you can see this Plutino, which is the orbit like Pluto, they will concentrate on this part of the sky. And other 2-to-1, 3-to-1 will concentrate on that part of the sky. So we sampling part of the sky to cover different kind of the population. So in this B1 field, we don't have many resonance objects. So we can only search for the classical Kuiper Bell object. And this classical Kuiper Bell object is seen to be the most primordial planetesimal in the solar system. So we would like to see the size distribution of this particular kind of the Kuiper Bell object. So we first analyze this B1 field with a shift and stack. So here is a illustration of the shift and stack. So the object can show up in this pixel, but it's too faint to be seen from the background. And the object is moving from the second frame, it's moving to another pixel, and the third frame is moving to another pixel. So because the thing is moving, so we have to we can co-add this image to get deeper, but because the object is moving, so we have to shift the image for each frame with the rate of the object. So we can stack the signal on the same spot, that signal can increase. So because we're doing that, right, so the objects remain in the same spot, the moving object remain in the same spot, but the stationary source is moving to another spot. So if we just stack that, the original image, the single epoch image, you will see a lot of stars, they become streaking stars everywhere. And that's doing your pixel. So before that, we have to cutting out the image. So the traditional way, the good way to do that is you do the differential image. So you take a lot of image and make the template. So those template only have the signal of stationary stars. Then you take your image, your single epoch image, to subtract with this background, and you can get this. So the remaining things are the transient. It could be asteroid, or could be cosmic ray. So, but doing this differential image is not that trivial, right? So there is a sample. So you somehow can do something wrong for the differential image, because we're trying to minimize the residual of the two images. So it's a minimization problem, but it could be go wrong to the other. Well, it's probably go to the local minima, but not the global minima. So you do the wrong subtraction and get this. So we are thinking that this not usually happen, but we still have some chance. But if you mix this this bad differential image into the shift and stack, you ruin your whole stack images. So there are a couple of ways to identify this bad subtraction. For example, you can see you can try to calculate the residual or the chi-square of the images. But the problem is that the standard deviation or the variance of the image it can be different by image, because for every image you have different background. And you can say, well, we can identify how many sources on the images, because the correct subtraction should have less sources. It's also true, but the problem is that it's also depends on the field. some field do not have many stars, some field have a lot, right? And even you have a good subtraction, they still have some residual. But it's somehow quite obvious by eye to see two different, the good one and the bad one. So we see, well, we can use human eye to go through every image, or we can try to train a machine to instead human eye to look through these images. So that's why we use the CNN, the convolutional neural net. So the CNN for this one is actually very simple. It's not very deep. So we have we have 3 convolution there, and I add some dropout to drop some useless feature. You can hidden feature. You can say that. So what I did is that we put the image through this neural net, and somehow give you evaluation of the scope. And you can see the good differential image and the bad differential image have quite different scope. So we can do the cut here to make sure that every scene are clean. So that's the first neural net. So after that, we can shift and stack. So you can see with the right rate of the motion, you can identify the sources. But if the moving rate is, if the stack rate is different, it's not correct, it's a lower signal. But the problem is that there are many sources. After differential image, you can see even good differential image, you still have wrong source, not a good sources. So that's we use the second neural net. So the second neural net is trying to find the PSF shaped scenes because our capable object is not the extending source. So it's very close to the PSF. So this neural net is done by Kevin Napier. It's our PhD students. So we use the tool set to training. One is that we know this differential image. We know the real, we after this differential image and we shift and stack, we should some capable object should show up. But we can reverse the shift and stack rate. So we stack the image in a non-physical space, non-physical rate. So which means if anything show out in that rate, it cannot be the capable object because we shift the rate totally wrong. So let's create the training set. Let's create a training set to pure junk. And then we know we put the fake source in the image. So we know where is the real source. So we have pure junk and pure correct sources. And there is another neural net using the training set in the AutoScan. AutoScan is the machine learning model to identify the correct training source in dark energy survey. So they create a set of the training set, and they have real source and also have the junk. So we use that to train another neural net. So if these two neural nets agree to each other, we say it's the correct sources. So the neural net is also not complicated. It's only 4 layers. Yeah, this one is only 4 layers. Both of them are only 4 layers, I think. But the result is quite good. And then we have third neural net. So after we identify the real sources, it still have some junk pass through. But we know because it's we know the shift and stack, if you have the correct rate, you get sources, right? If the rate is not 100% correct, you still get sources. So it creates this nice radial pattern For that one is have higher signal. So for lower signal, you still can see the radial pattern. So the third neural net is trying to look at this radial pattern. And surprisingly, we don't need to very complicate convolution neural net. It's also have only 3 layers of the convolution, and then the dense layer, and you got a result. So the result is that we can somehow reach 26 to 26.5 magnitude. So for the dark energy survey limit, it's about 23.5. For the LSST, it's projected to be 24.7. And then we have this outer solar system origin survey. It have the limit magnitude about 24 to 25 point something, 0.2. But now we can shift and stack to get a 4 hours exposure on one spot, one point of the sky, and get the deep depth to the 26.5. So we find thousands of the TNO. So here are 2,000 of the detections. Some of them could be the same TNO, I think, but it's detected for twice. And we have some Bayesian framework to weight every sources. So the weighting is quite interesting. So we have, so after this 3 neural net, we got some candidates. So we have many people to vote if this one is real or not. And then we mix with this reverse shift and stack, which we know is pure junk. Some of them look quite real, so the human can be fooled. So we can use that to test the false positive rate of each voter, each human. And then we know this human's false positive rate and this human's efficiency, so we can rate that. So we can give each person a weight. So if this one, for example, the person one have very high false positive rate. So if he say this thing is real, it's probably only 50% real. So we use that to weigh the every detections. So we can somehow have this digit point, because it's not every weight at one, right? So if 3 persons say these things are real, the weight will close to 1. But if only 1 person say real, 2 persons say it's not, so the weight is probably 0.1. So because we can go to 26.5, we somehow can get the size distribution of the object from to this limit. So here is so we're trying to select the pure co-classical object. So now we get the co-classical object size distribution. So the finding is that the co-classical size distribution is somehow going to flatten in the fin end. So we're not sure it will turn over or not, but it means if we go even smaller, we will not find a lot of things. And this result somehow, this result is consistent with the Kavalas et al. So they use OSAS to this limit. So they have quite good bright end constraints. And we do not have that good bright end constraint, but we have very good in the middle. And then if we use this, we add this Bernstein 2004 result, which is using the Hubble Space Telescope in 2004. So they also do the shift and stay on the sky and can go to the Mach 29, and they only discover 3 objects. So if we put that in, you can see this thing is actually bent over to get flattened. we think it's probably a sign that the co-classical object is less collisional evolution. So they form in some size. They cannot form too small, right? So they cannot be too big. So it's just a right size. And it's not evolve a lot, so it did not generate a fragment to fall out the small end. It's also do not collide to each other to become bigger, so the bright end is also dropped. So we think that's the hint that the co-classical Kuiper Bell objects are real primordial. Okay, so that's why my experience on the machine learning. So what I learned. So the lesson one is what exactly the machine learning is. So if you ask everyone give you an answer. Right? I Google, I got some answer from the Wikipedia, or from the dictionary, from IBM, the ChatGPT, also give you the definition, give you what is machine learning. It's a lot of things, but I feel that it actually is very simple. It's a way to solve the optimization problems. So if you have a data set, right? You can try to fill out. You say, well, you think it's a linear, so you fill a line, and the model is a line. So you get the best. You're trying to get the best fit. So you can minimize the chi-square to get the best fit. Or if you go to the Bayesian way, you're trying to maximize the likelihood of this line. So machine learning is just give you a kind of model to optimize, to minimize the residual or maximize the likelihood. Then you can fit the data well. So I feel that it's actually kind of the engineer approach to solve the problem. So if you use the science approach, you can get well balanced things, and you can just use a tab to fix that. So yeah, so the machine learning model is not necessary. It's probably not physics, not science motivate, but it somehow work for your data set. So it's somehow like this. So but if that's true, right? It's an engineering approach. It's not a real science approach. It will have some limitation. So my lesson two is that you have to understand the model, the limitation of your model. So we know that every model has a bias, right? Because we selected the sample could be biased. And also because you're trying to use this engineering approach. So if you're trying to do the things is outside your training set, it can go wrong. So I think this is an example. So you're trying to optimize a bed for human, but the human have this size and they somehow sleep in this position. So you create an optimal bed for the human, and it somehow fit that position well. But if you flip, you just fall down, right? So it's kind of overfitting. Yeah, so the good model is that you have to well balance, so you can do well on this. But if you overfitting, you probably do very well on your training set, but you cannot predict well for the real data. But still, it's overfitting if your real data is still in this region. It might be okay, but if it's outside your training set region, it will be totally fail. Right? So we have to understand the limitation of our model. So here is another example. Yeah, I encourage everyone try this web page. It's fun. So it's tell you how this neural net work. So for example, it solve the easy problem. So we have two set of different sample. Can you separate them using neural net? So for the first sample, it's quite easy. It's quick to converge. So it's an easy problem. So this is also a quite easy problem. And this is also easy. So the real challenge is this one. So you can see the simple neural net just cannot converge. So one solution is that you can try to go deeper. You create a much deeper neural net and hope that the thing can converge. Well, it's not work very well today. Okay, yeah, you can see the thing is become better, right? Is the neural net is trying to figure that out with your sample, your training data. And it's from this spiral shape thing. So you can see the things start converge, have better prediction. But still, you can see that even that we know if we extrapolate this shape, here should be blue, but neural net don't know. You can just do this one. Or I think the better way is that you don't need such deep neural net. You can add many feature because you know it's a spiral shape, it should be something around the angle. And so you maybe put some sine function, it could work. So yeah, so it's converge faster, right? Because you put the correct feature to help the neural net to figure it out. So you can form this spiral shape. But still, you can see the limitation of this machine learning model because for human, you can easily to see, well, it should be extend to here. So this part should be blue, but the machine don't know. Yeah, you can take this QR code, it will lead you to the TensorFlow playground. But I think the real solution is this. So if we choose the right coordinate, it's easier to get a good result. So I will say, well, it's a kind of engineering approach, but this is science. So we know it's the spiral shape, right, in XY position. But if you put that into the right coordinate in the polar coordinate, you can see it's just two lines. So you can easily to separate these two things. And it's somehow a very difficult problem for the neural net in the XY position. So you have put a lot of training time to figure that out, and it even cannot do very well. But if you put that into a right coordinate, you can also put this into the machine learning, right? The machine will give you the result, correct result in seconds because you're using the correct coordinate. So sometimes we can think about to put the more correct, I mean the more to put in the correct feature to help the machine to find the converged answer. So that's why I learned. So how can we apply that to the daily life? So we know this ChatGPT is very popular now, right? So I can even ask ChatGPT to write me a paper. So it did write a paper, start from the abstract, the introduction, the formation history. I asked him to write the Kuiper formation. But does that mean I will lose my job because my job's writing the science paper, but now ChatGPT can do that, right? So I think that it is not that easy because we have to know the limitation of this machine learning model. So we know ChatGPT is reading a lot of things. It read a lot of things much more than me. So he have very knowledgeable. But the problem is that the training set is somehow it cannot train for, you cannot put a future knowledge to training the ChatGPT, right? So his knowledge is somehow limited in some epoch. So it somehow cannot get a new knowledge. So it can only give you an old thing. So that's one reason that the ChatGPT doing well because it read a lot, but it also cannot create the new things because it never get a learn. And the ChatGPT is also good for writing the code. So here is that I told ChatGPT to write a PSF fitting code. So you actually write a code to fit the Gaussian function. It's pretty well. So I think that's a good start. So if we have any problem to want to write a code to solve, we can ask ChatGPT to do. It will give you a good start, and then you can modify the code. And it can also the AI can also plan, right? So it somehow plan quite well. It's generated by the Stable Diffusion. So you can guess what is this. So I think it's a solar system in Van Gogh style, and it's somehow like the plan information. But the AI still has its limitations. So here's an example. So for my friend, so he asked the ChatGPT to do some math. So the math, so here is Chinese, but so the math is that if we have the Cartesian coordinate, I would like to rotate that. So one is the square, so it's equal scale in the X and Y. The other is different scale in X and Y, so it's a rectangular coordinate. So how to rotate is how to get the rotation matrix. So the ChatGPT say, well, you can do that. Well, it's a correct rotation matrix, right? And in the rectangular coordinate, you can do that, but it somehow looks like the rotation matrix, but you can see something wrong. So you can see the scale here, but it's in the yeah, it's just not just wrong. But it's making the equation looks like the equation. And it's something, it's not just ChatGPT. So it's also another AI model, Stable Diffusion. You can make the good plot. So you ask him to make the Chinese style plot. It's make this keying is quite well. However, the Chinese style plot also have a character. So it somehow make out some Chinese character, which doesn't make any sense. So I think the problem is that the AI, they learn a lot of things, but they know the correlation, they don't know the causation. So it can make out something very similar to the Chinese character, but actually doesn't mean anything. It can make out the math equation looks like something, but which is totally wrong. So I think that's a limitation of your daily AI. So I think the final conclusion is simple. So using the AI is good. I encourage everyone to using this machine learning in your work, but you have to think, you have to watch out because the machine do not have brain, and you have to use your own. Okay, I think that's all. Thank you.
Yeah, thank you very much, Everett, for this very interesting talk. Obviously, you have brains, lots of brain.
I hope so.
All right. Anyone have questions? For now, I'm sure that they could write to you also, but they could ask you questions. But I have one because which interests me. You mentioned about your DEEP project.
Yes.
So you say you have you have found how many? You have found 2,300 KBOs.
Yeah, I think that's for the individual object, it should be around thousands.
And you say you could go down to magnitude limiting magnitude 26. And how does that translate into size?
Ah,
I mean, can you see a kilometer size object?
no, so our limit is here, right? So it's about 30 kilometer.
Oh, still 30 kilometer. All right.
Yeah.
And can you then derive a size distribution? Here you only have a magnitude distribution.
Well, it's edge distribution because we don't know the albedo, right? So we can option. Yeah, so it's actually kind of size distribution. We present in the magnitude, absolute magnitude.
Well, because I'm interested in if you could have a size distribution, you could extrapolate to smaller objects. Then one could predict how many small KBOs can the TAOS2 project can find.
Yeah, I think that's true. So you can extrapolate this, but we are not sure it will turning down or it's keep this. We don't know yet. Yeah, but if this Bernstein 2004 result are correct, it looks like it could be turned down, right? Because we are passed through this upper bound of this result. It could somehow turning down. And I think that's motivated by so there's a formation theory called the swimming instability. So you can create certain size of the planetesimal, and you can also find that the planetesimal is very likely to create as the binary and flat. So in this swimming instability, and we know this error curve is flat, right? And this binary and flat. Yeah, so this theory somehow become popular because it predicts things that something like error curve, and it's also explain the high binary rate in the co-classical hyperbell. And now, and it's predict that there are not much big things, which is true in the offset sample. And it's also predict that there are not much smaller things. So which is also true from our result. So this so the people, the streaming instability people see our result is very happy because it somehow consists with their prediction. Yeah, so if that is true, the TAOS probably won't have too many event rate.
Yeah, too bad.
If they're looking for the co-classical object.
Because when they start planning this 20 years ago, it was there was a time that you have a very steep slope.
Yeah, right.
And then slope keep on coming down. They're always behind the slope.
Very unfortunate.
Very unfortunate, yeah. Anyway, I can see some people here. I saw the name Tom Lin Jianxian. You have questions? Because Tom is also a machine learning expert, I suppose.
Yeah, Tom, probably more expert than me.
We have a couple, machine learning expert here too. You could raise your hands, or you could write down your question on the chat box. If not, yeah, I see that okay, it just says that if you have questions, you can write it down, and in the chat box, and we could catch up with you, just in case you couldn't ask the questions on right here. If not, and then we would end the session now because I have to go to class. I'm sorry, Simon. And then I think that please look at the advertisement for next talk. It should also be very interesting. And just to make an advertisement that I think I have invited Dr. Gordon Yip Gordon Yip, he's working on the aerial project at UCL, University College London, doing machine learning. And he will be giving a talk, I think, in September. Yeah, so pay attention to that too. Okay, thank you so much, Edward. Yeah, I think it's very precise talk, as you always do. And then and good luck. And I look forward to reading the paper Napier et al. Right?
Yeah.
Okay, thank you again to everybody.